we'll continue to do this even after we're all no longer working from home and back in the office. We will commit to doing this for you. So that being said, that's what we do. That's who we are. I think we can get started. Today's topic is ETL best practices, performance tuning, and troubleshooting with Azure Data Factory Data Flows. Data flows within Data Factory, for those of you who are new to it, is really the data transformation or the ETL piece that's visually oriented within Data Factory. There is a whole set of capabilities and script behind that the UI produces. We can touch on that a little bit. Probably won't get too deep on it. And there's a lot to cover, so I'm probably just going to start blasting through some of the material. I want to first, before we do that, go over an agenda and a quick high-level view of architecture for data flows, so you understand. It'll help you, I think, in terms of troubleshooting, in terms of performance tuning your data flows. So think about data flows when you're building a factory, when you're in a factory and you're building a pipeline. Think about the flows as the piece where you're going to go for your pipeline to transform your data. You're going to visually create that logic. You're going to manage and monitor those visually. Very much the orientation for a data engineer who is needing to create a lot of ETLs and scale those out as well, because the data flows within Data Factory execute on Spark. So very important to keep that in mind as well, that Spark is the engine for data flows, and so a lot of the knobs and levers and different feedback you get will have a very Spark flavor to it, and there's a reason for that, because it's using Spark in the back end. So we're going to talk a little bit about how to set up those compute environments for data flow using the Azure Integration and Runtime. I'm going to go over a series of performance tips for optimizing them. Partitioning is very important in data flows because, again, it's Spark and it's a distributed compute system. How to monitor those, we're going to look at some execution plans and then management of that performance. Some troubleshooting, common errors, and then at the end, when Dan and I do these tradings, we swap off who presents, who answers. Dan is on the answering part of the session today, but he had a couple of really good examples of the monitoring UX that I'll show, and just kind of talk to his material at the end before we go. And we should have time to get through most of these. We did this one internally yesterday, and a very similar session. We made through most of it, so we should be okay. We'll see how things go. All right, so first, very important to get a good idea from a sort of a 40,000 foot view of how the data flow service works within Data Factory. So let's step through this. Think about this as a waterfall, or steps on a ladder. We're going to start, that won't be a ladder, this would be steps. So we're going to start at the top left, and then we're going to work our way down to the right, to the bottom right, okay? So you start as a user of Data Factory. You're going to start by designing a data flow graph, and you're going to do that in sort of what we consider a construction paradigm, slightly different than the pipeline or control flow piece of Data Factory, if you like to use SSIS lingo. And that's because we feel like the pipeline within Data Factory is really oriented toward workflow and workflow designers. And so this gives you the ability to, as a designer of workflows, to be able to build DAGs, direct acyclical graphs, and that works really well for workflows. But when you're going to build a data flow, you're going to focus really on logic. You're really building code. And so as a code builder, I'm going to give you a building or construction paradigm for that. And that's why you see that sort of a construction paradigm. You're going to essentially continue to add different steps to your logic as you go. So you're going to pull some data into a staging area. In most cases, you're going to transform the data. You're going to aggregate it, join it, and then at the end of this journey, you then sync it, or have it put the data in a destination. Every data flow, when you execute it from a pipeline, must have a source and a sink. That's mandatory. Source is mandatory for debugging. Sync is not. You can sit there in debug mode in data flow, and you can just use it as an analytics tool. You can use it as almost like your cloud-based data analyst tool. You can do pivots, you can profile your data, you can do all those kinds of things. You can aggregate your data without even landing it anywhere. So you design that, and then what this designer does in Data Factory is generates script behind the scenes. The data flow script is really the brains behind data flow, and it is the set of instructions. It's really metadata. It's not really code. It's really metadata, but it produces a script that is that defines the transformation for your or the logic for your transformations. And so you could actually generate, you can write the script yourself. You don't even need the UI for it. We have a set of APIs, PowerShell supports, .NET, and so on, that actually would allow you to just take the script and to send that into a pipeline as an activity. This is not JSON, so Data Factory is all based on JSON, but the JSON payload that includes your pipeline includes in it an embedded version of this script. So when you look at the JSON for your pipeline that has a data flow in it, you will see the script hidden in there. It's not hidden in there, it's plain text without any credentials, but it's plain text, but it is fully encapsulated inside of a property on a single line. You can view the nice looking script in the UI. I'll try to get a chance to show this to you as we go through today. Anyway, so the rest of this is described in the slides. These slides I will put as a link in the published video when we're done, so you can get these slides. There's only 6 slides, not a whole lot of material in it, but this is a good, helpful picture. Maybe even Dan and I should kind of spruce this up a little bit and put it in our docs. I think this is helpful for you all from a performance perspective. Anyway, so what happens, and this is very important, is once you generate that script from the UI, or you generate the script manually by hand, Data Factory from a pipeline will send that script to a Databricks cluster, and that Databricks cluster is our Spark environment, and we spin that up just in time on an on-demand basis. So this is where you start to see your data flows then in production from a pipeline will pause for 5-6 minutes, whatever it takes, for that Databricks cluster to launch and to become available. That is the on-demand job cluster mechanism of Databricks that you're seeing when that happens. There are ways to optimize that by setting a TTL on the integration runtime. We'll talk about that in just a few minutes here. But that is what's happening behind the scenes. So once that Databricks cluster is available, that script is parsed out of the JSON and sent over to that Databricks cluster, and that is what is executed. So what happens is we have an executor job that runs on the Databricks cluster that is spun up. And this Databricks cluster is fully encapsulated within the Azure Data Factory subscriptions. In Azure, you don't see a bill for Databricks. You don't see that ever spun up. You don't touch it. It's completely encapsulated. It's hands-free essentially. You don't have to manage it. You don't have to keep it running 24/7. It's just in time, so it's very effective in terms of not needing to worry about a cluster. It's very effective in terms of economics. But what happens then is that when that spins up, we have an executor job that takes your script and it parses it apart, and then we execute your logic. And we can do things with that because we can holistically look at your logic, and we can say things like, okay, this you have a filter, you have a sort. These things would be very good to be pushed down really close to the source. Or perhaps we might want to leverage Spark partitioning. Even though you didn't set partitioning, maybe manually, we're going to use partitioning across all of the nodes available to us, and so we can do tricks like that to optimize your data flows. Now, if you're not happy with the optimizations or you want to change some of that within your data flow, I'm going to show you the knobs that you can turn and levers you can pull to do that, and that's where the performance tuning comes into play. And then at the end, after that's executed, and while it's executing, actually, this is the view at the bottom right, the monitoring view, is available to you both after the execution, so you can go back and look at the history, and you can look at any regressions in performance of your data flows. Think of this monitoring view as sort of your management studio, kind of looking at execution plans, if you will, kind of view for Data Factory of your data flow logic. All right, I think that probably pretty much sums that up. Let's start looking at some of these things and how you build these and tune these within Data Factory. So the first thing we're going to look at tuning. Let me go over these bullet items before I show you these things from Data Factory. But we're going to start with the Azure Integration Runtime. The Azure Integration Runtime is a concept within Data Factory, and we have many different types of integration runtimes, or what we call IRs. We have one for SSIS. We have one that's self-hosted, so you can run it on a VM or on-prem, and then we have the Azure Integration Runtime. The Azure IR defines how you work with compute environments and different environments within Azure specifically. All right. And specific to data flow, there is a section at the bottom that is an accordion that you open up, and you can define the compute environments that you want for data flow. Now, when you create an Azure Integration Runtime, this does not spin anything up. This does not start anything. An Azure Integration Runtime is a JSON definition, or essentially a set of properties that Data Factory will store and will look at and will read when you do things like start a debug session in data flow, or execute a data flow activity. All right, so it defines the compute configurations of your data flows. It can be used for both debug and triggered runs. So let me actually make a point on stating something here while I'm talking about this. Debug within data flow requires you to start the debug session. That debug session can use a different Azure IR than a triggered run. A debug session in Data Factory for data flows is used both for your design time data preview as well as when you execute a pipeline from debug, that same cluster. That cluster is an always running cluster up to 60 minutes. So there's a 60-minute TTL by default that you cannot change for debug. If you are done with your debug and you don't want to wait for the 60 minutes to time out, you just turn it off, and that turns off immediately. But we leave that running for you so you can sit in an environment where you are interacting with a cluster environment so you can see the preview of your data. So I'll talk about that here. The debug session is a 60-minute TTL by default. There's a TTL setting on the integration runtime where you yourself can set a TTL for your triggered runs. The time to live only is honored during triggered runs. This provides you with your own pool of VM resources for Databricks on the back end for your data flows. And then what will happen is the VM stays warm, and when you issue your next sequential data flow, all that Data Factory has to do then, or all that really Databricks has to do, is just load the bits in the job and it runs. So that takes about 2 minutes. So it's a very good way to minimize the delay between your data flow activities. So let me complete these bullet items. I talked about that. All these things are enabled when you're in debug mode. Debug mode takes about 5 to 6 minutes to start up because it is also starting up a Databricks cluster. Turn it off when you're done so that you aren't billed for time that you're not using. So there's always this cost because this is a cloud service. Data Factory is a platform as a service. There is the concept of cost versus performance. Those things are somewhat in battling with each other, and you have to make a determination a lot of times of, if I provide let's say a memory optimized compute of 128 cores, that's an expensive compute environment, but it could complete my ETL very quickly. So there's economics involved in all those things. We'll talk about that a little bit more in a second. Triggered runs always use a job cluster unless you set TTL, in which case we can give you a warm pool that is just for you that you can use to execute your jobs faster. Alright, so bear with me for a second. I'm going to use the streaming software that I'm not very familiar with now to switch over to my Chrome. So give me a second. Let me do this and this, and let's see if that works. This should now make my Data Factory visible. That's not what I wanted. That's what I want. Oh, I did the wrong thing. Sorry. See that? I knew it was going to happen. There we go. So I guess I could switch over quickly to the comments just to make sure that you all are seeing my my browser now. Just let me know if you're not seeing. I'll tell you what. Somebody shout out, or Dan shout outs on Teams or whatnot if you're not seeing my browser, but I think I switched over to my browser now. So let's go ahead and let's take a look at some of these things that I've been talking about so far. So I'm in my data factory. I have the simplest possible data flow, valid data flow that is available, which is a source and a sink. There's no transformation involved in here at all. Now, what I want to show you is a couple of things in terms of what we've been talking about, in particular the integration runtime piece. And the integration runtimes are available under connections. So you go to connections and you go to integration runtimes. Now, there's a couple of different working models. I'll give you one that I think is very effective, and that is to create an Azure IR, at least one for debug and one for production. So if I am in integration runtime, I click Azure self-hosted, I select Azure, and then in here, let's first make a debug cluster. I'm not going to call it cluster. I continue to use the word cluster, but this is actually an integration runtime definition. So let's call it a debug Azure integration runtime, or a debug error. Error, not error. And under the data flow runtime section, you're going to see 3 different compute types. So the differences here are the different VM series that are used by the clusters in the back end: general purpose, compute optimized, memory optimized. In terms of pricing, so if you think about pricing first, compute optimized is the least expensive, memory optimized is the most expensive. When you're running in debug, if you'd like to save a little bit, compute optimized usually works just fine, because in debug mode, when you are previewing data and you're working in the designer, we do sample data, and I'll show you that. So you can use compute optimized, save a little bit, keep the core count around 8, maybe 16. These are added together, by the way, to give you the total number of cores. The first number is the number of worker cores you get. The second is the number of driver cores that you get based on these configurations. We don't go higher than 16 driver cores, but the number of worker cores exponentially increases as you go up here. Now, when you are so this could be your debug. Don't worry about TTL. Again, TTL for debug is always 60 minutes. Now keep in mind, if you use this configuration, compute optimized 8+8 for cores, no TTL for your debug, when you go to test your pipeline in debug mode, if you don't use sampling, you may run out of resources, because compute optimized has less memory on the compute VMs than memory optimized does. So just keep that in mind. I'll tell you what I use just for myself. I use memory optimized for my debug. I know Dan argues with me, says that's overkill, so that's fine. I'll compromise. I'll say general purpose then. Maybe 8+8 might be good for you for debug. Compute optimized will save you a little bit, and then memory op. So yeah. So let me just finish that thought. That's essentially your debug Azure integration runtime. Create that, and then come back in and create an integration runtime for your operationalized or triggered pipeline activities with data flows. So we could call this production error. All right, and then in this case, I would almost always recommend memory optimized. And maybe you do this. Maybe you have, most of these ETL patterns will be maybe a daily or weekly very large load. So for the larger loads, maybe you go up to 64 or even above in terms of cores. And no TTL for that, because this is like a one-time thing. You run it, it takes 3 hours to run, and you do it once a week or whatever. So this will give you a little bit more horsepower behind it. But then you have your incremental runs. So now I can call this production. I can make a third integration runtime and call it production error incremental. And then what I'm going to do here is I'm going to have a little bit less resources for it. So I'm going to save a little bit of money when I do my incrementals. And I'm going to do a TTL on that one, because maybe I run 3 or 4 of these in a row consecutively. So I'll set a small TTL of 10 minutes, which means I'll always get charged a minimum of 10 minutes billed for it. But maybe the data flow, the ETL itself only takes 5 minutes. So it's 5 minutes for each activity, and then the 10-minute TTL is what you're billed for. But this would give you the ability to both set the right performance profile as well as the right economical profile for you based on the different usage that you have of your integration runtime. Now for the demos today, I'm going to go back over to my data flow here called loans. And I have my data flow debug already turned on, so my design environment now has a live connection to a Databricks cluster. And if I hover over it, you can see that I'm using an integration runtime definition that I called as data flow cluster. Okay. And what that is going to do is that's going to give me a memory optimized environment. I think I set it for 16 or 32 cores. It's one of those overkill, oversized debug clusters that Dan doesn't like me using, but that's all right. This will at least give me an environment where now when I am in data preview, it will work just fine. So let me go ahead and do a data preview. We'll just take a quick look at the data for my loans file. And then when I am testing out the end-to-end pipeline, and when I'm in pipeline and I click on debug for the data flow, it'll use the exact same cluster. So when you have a activity, let me actually walk you through how you set an activity on your pipeline. So this is a pipeline. Notice the difference sort of design environment. What happens is you can take your data flows directly from your data flow Explorer over here, your resource explorer, and you can just drag that over into the pipeline viewer. And my thinger is not working, and that will show it, but for some reason, give me a second, I don't know why that's not showing. Let me do it this way instead. Well, that's weird. So you can take your resources and drag them onto your design surface, and that data flow will show up on there. I can guarantee it. I don't know why that didn't work for me. But you can always add it this way too. So when you have multiple, in this case I have multiple data flows on my pipeline, so I would sequence these by using the arrow between the two different activities. Now what would happen is each one of these data flows on my pipeline allows me to set the different Azure integration runtimes. So the different Azure IRs that I had set from my integration runtime configurations before are available to me here in this list. Each one of these can use a different IR, so I could say maybe this one requires more resources than this one. So I'm going to give a large data flow Azure integration runtime cluster to this one and a small one to this one. However, those integration runtimes will only be used when you actually trigger this from a triggered run. So the pipeline has to be run from a triggered run. Either trigger it now, which means just execute now from the pipeline environment, or you schedule it and you create a trigger, an event-based trigger or a scheduled trigger or any other trigger types that we have within Data Factory. Then it'll use this job cluster down here. If I set a TTL on this Azure integration runtime and I use the same one for both, the same integration runtime for both, so for example, if I say the data flow cluster that I like to use, if I use it for that integration runtime for both of these, and I have a TTL set in there, it could be as simple as low as 10 minutes. Now when the second one runs, this will only take 1 to 2 minutes to start up because the cluster is already warm on the back end, so the compute's already there available for me. Otherwise, if I don't do that, if I use a separate integration runtime, it's a job cluster, and so it'll take 5 to 6 minutes to spin that up and start that up. So keep those things in mind when you look at the performance profiles of your data flows within your pipelines. Now, if I go ahead and test this from debug, and I'll tell you what, let me just go ahead and do that. So when you click debug here, that's why. That's why it was messing up on me. So let me actually close this out. I was in a weird state for my previous demo. So let me go ahead and let me just make a new pipeline for this. So let's go ahead and do a new pipeline. And I will pick a data flow. So my data flow is called loans. I'm going to add it in here. And it is called loans. I'll show you what the data flow does. We're going to talk a little bit about partitioning files and working with delimited text in just a minute. Okay, so by the way, the auto-resolve integration runtime is an Azure integration runtime that is the default that you get with every factory when you start a new factory. You can use this for debug and for executing your data flows, that's fine. It just doesn't have any particular configuration in it. You can't edit this either. You can't modify. You essentially create new integration runtimes as you build your own pipelines and use other integration runtimes. This is the default. This comes with every factory. You can also set, when you have this set, you can also change the compute type and the core count right here for each of these activities. So you don't have to use the configuration from one of these other integration runtime. So for example, back against that data flow cluster, that makes those options disappear. But if I'm just using the default, the auto, I could say, you know what, this run right now is going to use a lot of resource, so I'm going to go with a memory optimized 64 on this. So you can set that here as well. Again, this is only going to be read and honored during during an operationalized, triggered, scheduled run of that pipeline. So when I clicked debug there, this is going to run pretty much immediately because it's going to use an already warmed up debug cluster because I clicked the debug button. So it's not going to look at those integration runtime settings, okay? So this is what I was showing you earlier in terms of being able to monitor your data flow live interactively. So this is running now. This has been running already for 20 some seconds, right? Yeah, 31 seconds. So if I click on the eyeglasses, I can dig into the UX monitoring of that data flow, and you can see the status is running. If we were still trying to connect into a Databricks cluster, it would say that the data flow status is acquiring computes. And so it only took 11 seconds to connect into the execution of a Databricks job. So that was very fast. And then you can refresh here if you don't like. This is the auto refresh is on, but you can always click refresh to go ahead and refresh this faster. So what this is doing, let's take a look at this loans data flow. Let's take a look at maybe some of the partitioning options and the way that you would work with data in data flows to optimize. So my data flow is just a source and a sink that has some mocked up loans data that has a fair amount of columns in it. It has, if I click on inspect, it has 74 columns and has a fair number of rows in it as well. I think it has about 890,000 rows in it. So it's a pretty good size file. That pipeline completed. All I'm doing is going source to sink. And this is super simple, but I want to show you something. When you're working with delimited text files, leaving current partitioning sets for the optimize. So there's an optimize tab on every transform in data flow. This is where you can go to set some configurations to set your own optimizations for your flow. So I just leave it set to default, and with file-based transformations, essentially lake file-based ETL with data flow. This is the most effective. This essentially tells Data Factory to use your own optimizations on your executor job, leverage Spark, and use your best guess on that. I'm going to show you how to tell it, give it hints to tell it what to do, but without doing that, that's what this does. And so from when you get to the sink, this is where for a file-based sink, you get these options to be able to have different file naming options for the output. I just left it as default and I said clear the folder. So clear the folder will take a little bit of time because I had, I think, several hundred files in there already. This was a look at my last run from my, actually I can't show you that because that is my Explorer. I can show it to you from here. So we did get a bunch of file outputs just from this run, but I had about 100 files in here before. So when you say clear the folder, what that does is that tells Data Factory to go ahead and remove the files from that target folder. My target folder is defined in my data set. My data set is called folder out, and the path is output demo out1. So it's going to clear that folder. Now be careful with this option, especially in production, because you may not want to clear a folder. You could be writing to a folder with other shared files in there, and you don't want to necessarily bomb all that stuff. But when you're testing and doing perf testing, this is good to do. It gives you the ability to clear it out, keep it clean, and then you can look at the output from your execution. Okay. The only way to get file output is to run it from a pipeline. When I'm here in data flow and I did this data preview, I'm in the data flow designer and I hit data preview. There is no writing of any data. This is just a snapshot of what is in memory in data frames from that Spark cluster at that point in time. So the pipeline completed, let's go back to that now, and let's take a look at that monitoring view. It's going to be a very simple view because it is all just the one single, or essentially the source and the sink. There's not really any transformation going on in here, but let's take a look at it. So it took 1 minute and 35 seconds. 11 seconds was spent acquiring the cluster. The source transform had 64 partitions. So if you notice, I said use current partitioning. I did not specify a partitioning scheme. But Data Flows gave me 64 partitions, 888,000 rows. I was close on that number. The 74 columns. And to read the data from that file took 7 seconds. By the way, these are all called stages within Data Factory's monitoring view. When you look at this execution plan, we call these stages, and that's why you see a stage time. And the reason is for very complex transformations and very complex data flows, we group together the logic and the actions that you're doing against your data. So we don't give you timings for each individual transformation. We give you timings of a stage of transformation. And then, so this was all based upon the optimizations that the data flow itself did. And so those 64 partitions were then passed through to the sink as well, which means I'm going to have 64 files. So if we look at my file outputs, I can go here to do that. You're going to see 64 files, and they're all going to have a job ID, ugly file name associated with each partition. .csv. So if you don't like that and you want to give a name that's a little bit more meaningful to it, you can absolutely do that. I just want you to be aware of the impact of doing that. The fastest way of working with files, the best performant way in data flow, is going to be to allow Data Factory to just go ahead and name those partitioned files. And then if you like, what you could always do is you can yourself go back and have a process that goes in and renames those after it's done, but let it do its thing and generate those files. However, if you'd like to coalesce and bring those files together into one, we can do that for you. We call it output to single file, and then you just give it a file name. Notice the warning banner you get here, which says that there is a performance impact of doing it because we have to coalesce down to single partition. So you have to click that button to use this option. That's kind of our way of saying, hey, just be aware, you're now going to use a single partition. Okay, so I'm going to go ahead and run that now. And I'm going to, let me clear the folder as well. So remember, if you're going to clear the folder though, I'd recommend you make sure you don't do this in production unless you absolutely have a reason to do it, which is fine if you do, just be aware of it. And in addition to that, it's going to take a little bit longer. So if you're looking at performance, essentially execution plans, you're looking at the monitoring view, there is some time taken up and clear the folder. So let me go ahead and execute this in the pipeline. Before I do, I want to show you what I mean by that. In the monitoring view, you'll see two things on each sink. You'll see both the time it took to actually execute the transformation within the sink, which was 7 seconds, but the time it took to actually process that and write it was almost a minute. That's because of the I/O involved of writing the actual data, plus in my case I had clear the folders. There is time taken up for that. Okay, let's go ahead and debug this. This will run that now against that same data flow, but this time I'm going to be writing to a single file. Let's take a quick sip of water here. Now, while that's cooking, this will take a minute to run or so. Let me go back into this and show you one more thing with file types before I move on to database types. The other file name options are going to work a little bit better for you if you need to have a name structure for those output files. One of the ones that we like that works pretty well is pattern. When you click on pattern, and by the way, I just realized I might have clobbered what is running on my my pipeline right now. We'll see what happens. But when you click on pattern, you can do something like I did here, which is I called my file loans square bracket n square bracket .csv. The n is a special character that or is a special syntax that we use to represent the partition number. So this would create a nice output of loans 1 through 64 .csv. So it gives you the same ability of keeping that partitioning without needing to coalesce to a single partition, while giving you a meaningful name of your files. So that's always a good option that I like to throw out there as well. I'm not going to touch on the other ones. We can do the other options another time. And then from an optimized perspective, there is one other thing that I would just kind of recommend you looking at, and that is, first of all, when you switch to output to single file, single partition is set. If you're going to try another option like this pattern, make sure you can back into optimize and either go back to current partitioning so you get those 64 partitions, or go ahead and set the partitioning yourself. If you understand your data very well, you can start to fiddle around in here, and you can do things like create a partitioning based on hash. You can do generic round robin, so you get equal distribution across partitions. For example, you could set 200 partitions and whatnot. We do have some guidance in our performance guide that is in our docs of the number of partitions being based upon the number of cores that you have set for your data flow compute environment. So I'll let you go ahead and read that, and I'll put a link to that in the docs as well. So you see back here on the pipeline that I was running to coalesce to single file. Let's take a look at what the output looks like right now. So if I refresh this, you see that it did clear out the folder. And it is still running. So notice what it did. So it got all the way through the actual transformations, or the actual logic, and it cleared out the folder. And right now it is writing out the files and coalescing down to a single file. And so that takes time. And almost all this time is taken up just in the output to single file. So you can use single file, just be aware of the performance implications on that. Let me take a look at how much time that we've been running this guy now, and it's up to 3 minutes. And it took what was a little over a minute, I think it was, to allow all partitions to be written as files. I'll just let that cook in the background. If it doesn't complete by the time I get to the next demo, then I'll just cancel it, but let's see if that completes. Let's take a look now, again, switch gears a little bit and take a look at some database optimizations now when you're writing and reading from databases. So I've got an example over here called large joins. And let me actually, give me 1 second. I'm going to go into my streaming software here. I'm going to quick add another share here because I want you to see my SQL Server Management Studio. So I just have to go here. No, I have to create new. Give me a second. I know I can figure this out. And go to Management Studio and click OK. And then I can hide this. Okay, so you should be seeing my Management Studio now. Dan, just give me a Teams shout out or anything if I'm goofing up and you're not seeing it. But here's what I want to do. This is very common that we see with ETL and Data Factory with data flows when you're working with Azure SQL Database. So in this case, I have a join that is a multiple inner join. So I'm combining these 4 tables together. My main table is loans, and then I've got loans demo, loans partition, loans no partition. Kind of a contrived demo, I know, but I want these all to create these 3 columns, these 4 columns, sorry, and 1 column from each of the joined tables. So let me execute this join here from Management Studio, and I'm already getting data back. Now, I think the end-to-end execution time for this data flow, I'm sorry, for this join is about 15, 19, 20 seconds is usually what it takes when I run this. There you go. It took 15 seconds to run, okay? So remember that. Now, when I go into my data flow, so let me get back to my software thingy here. I have to say, share my Chrome, take away my SSMS. Now back to my data flow. This is the way that you would model a similar sort of join within data flows. And the way that I had to do this, I'm going to zoom in a little bit here. The way I had to do this was you can only do 1 join table to your primary incoming table. You do a left and a right within data flows when you add joins. Okay, so I had to do 3 separate join transforms, which works just fine. I just say, here's my first join, my second join, my third join. I'm doing the same thing I'm doing in the code, right? I'm just saying here's an inner join, and here's my matching column, and here's my right-hand side. That's all. So the way I did this was I have my source, which is my loans database. Okay, it's a SQL source. I have not set any optimizations on it. I'm saying use current partitioning. The same thing in my sink. I'm saying use current partitioning, and I'm writing out to a file. I used what's called a new branch transform, which just takes that input data, that source, and it just duplicates it. over and over again. So I duplicated it 3 times. And then I'm joining each one of those together. So this is the way that I modeled that same inner join syntax from T-SQL, okay, as an ETL within Dataflow. Let's take a look at what that looks like when you execute it. And by the way, my pipeline for coalescing to single file, there you go, finally finished. It took 5 minutes and 46 seconds. Let's look at our output on there. Beautiful, right? I got my one single file, but I had to pay a penalty to do it. So that's all I'm trying to say with that. I think that got my point across on that one. So now let's move over to that large, I call it large joins. Okay, let's go ahead and run that. So I call that large joins. All right, remember it's not going to use this setting. It's going to use the debug setting when I run it from debug here. It's called loans. And let me actually, I realized that because I put a new data flow in here, I call it loans. That bugs me. So I'm just going to call my activity data flow. There we go. So now this will run my large joins. You can just switch it here in the data flow name when you're doing this. Let's go ahead and debug. This is a very common way to debug a number of different data flows that you have. So this is going to run that join. Now that join, the 3-way join within Management Studio took 15 seconds. I'm going to run it with 3 different join transformations in data flow. And let's see what happens. Now, of course, it's not going to be 15 seconds, right? Because there has to be data egress from SQL database. There's going to have to be in memory. There's going to be, a job execution has to be stood up. There's going to have to be in memory data frames created. There's going to have to be some shuffling of data, some broadcasting of data, and then the join. So that takes time, of course. But let's see what we get. So this is at 41 seconds. Of course, it's already taken longer. Let's open up the interactive live monitoring and take a look at what's going on. So the clustered startup time was 10 seconds, which is good. And we are still in the first stage, which is, if I click on it, you can see that it is these sources. So it is still acquiring the data. Now, while it's doing that, I think it takes about 2 minutes to run. So while it's doing that, I want to show you something else within these database types or within these transformations. I'm doing these joins. In each join, there is an operation that Spark does as a distributed system that's called broadcast, or essentially taking the data from your join criteria, taking the data that you're going to be joining and pushing that into memory in each of the nodes. So it's going to distribute the data and it's going to put it in memory. You have some control over that and optimize on joins, lookups, and exist transformations in Data Factory. And that's called broadcast. Now, just FYI, this feature is going to change a little bit in a couple of weeks, and Dan and I will send out some notices on that and some updated documentation on it. But right now, broadcast is always on. You can turn it off, is one of the features we're going to add. Broadcasting will take up memory. This is why I recommend using memory optimized when you run in production, so that these joins can work a lot faster and can get pushed into memory. But you can explicitly say push the entire left side or push the entire right side into memory. If you have a lot of data, you got to have enough memory for that data to be compressed and stored in memory. A lot of times the right hand side is smaller, and so it works a lot better if you do that. I just want to call that out to you. Otherwise, by default, Spark will try to. Okay, tries to optimize that way. So this data flow completed in 2 minutes. So it took 2 minutes to complete that join. And what it did was, you will notice that if I go over to my sources, one partition. So the default for reading data from SQL in Data Factory is single partition. I will show you how to change that and how to improve upon that. But this entire stage of reading the data in took 51 seconds total to be able to read that data into Spark. Okay, and then each join occurred after that. Now notice how each join used a default partitioning in Spark of 200 partitions. So data got distributed, and if I had enough memory on those nodes, broadcasted down into those nodes as well. The joins themselves took 13 seconds each, which is funny because I think actually the total stage time was 13 seconds. And yeah, that was all one stage. So actually the joins themselves is a very comparable amount of time. So this is how you can read what's happening in your flow, and you can look at where you can optimize. So one way to optimize this I wanted to show you all is to use push down yourself. So manually tell Data Factory that you want to push that down to the database. And the way you can do that is you can conform, or oops, I don't want to do that. You can refactor this entire data flow that I did here. You can refactor that into a push down with 2 transformations. Okay. And on the source, what I do is I use a source query, and that query should look familiar to you. That is the same query I had in Management Studio. When you do that, Data Factory will push that down into the database, and my projection is still there. So I still get my projection because the projection is coming from the select portion of my query. By the way, you can do this manually in Data Flow as well by using the select transformation. The select transformation also allows you to set a projection within your flow, just like that. Okay. So I got my projection. Now I'm going to do one more thing to make this work even better. I'm going to optimize. So remember, I said that SQL database comes in as a single partition. I don't think that's effective, so I'm going to tell Data Factory I want to set the partitioning. Source partitioning is a specific type of partitioning only for SQL database and data warehouse or Synapse sources. I forget if we have this on Cosmos. I don't know if we do. I don't think we do. I just picked a number based on my number of rows of 880,000. I just picked 20. I would base this on number of cores. If you're going to have a lot of cores that you're going to throw at your compute, you can increase this number and it may work faster for you. But this is something that you can play with. That's a little bit more art than science in that case. But I said, give me 20 partitions, and I'm going to partition on a column with high cardinality, so I picked ID. And then on the sync, I don't think I set anything. On the sync, I just said maintain that partitioning, use current partitioning. Okay, so we've pushed down. We're going to push down the join, and we're going to set the optimization. Let's see how this one runs. This is the exact same flow, by the way. There's no difference in the logic. It's just how I sequenced things. So this is large joins copy, and let's debug, and let's see what we get. This is probably the last one I'm going to have a chance to show you. You know what? While that's doing that, let me show you one more thing. I'm going to go over to Dan's portion that he did. He baked something which is kind of nice that I want to show you all. I just have to go to the right thing. I think it's over here. Yeah, beautiful. So Dan has another example with SQL database doing the same thing using source partitioning. So he had this copy loans data flow right here that took a total of, if I look at the total timing on it, it took 13 minutes and 52 seconds. Now let me go back into the monitoring view to show you something. This is when you execute your data flow from a triggered pipeline. It took 6 minutes in this case to acquire the computes because it is a just-in-time, on-demand Databricks cluster that had to be spun up. I'm going to show you how to minimize that in just a sec. He then ran it with this data flow, which is source partitioning. So he did the same thing, of saying source partitioning. I'm not sure how many partitions he set, but we'll find out in just a second. He set source partitioning of 10 partitions. Okay. So you see that when you also then set maintain or use current partitioning, that same partitioning flows through to the end to that transformation within your data flow. And so what that means is he went from 13 minutes, almost 14 minutes, down to 10 minutes just by partitioning the data within his data flow. So mine already completed. So mine was half the time. It went from 2 minutes to 1 minute because I'm doing source partitioning. And I really simplified my logic. I had the entire join in memory. That took what was it? It took about 28 seconds, and then the sync writing was about 35 seconds. And that's it. So that's a way to do push down into optimize with SQL. So 2 more things, then we'll be wrapping up here in about 8 minutes. So let me show you something in terms of how to optimize now the startup time of the compute environment on operationalized or triggered executions. So let me go over to my magical streaming software again, and I will click on that and that. this to be here. Let me see if that's working. Okay, cool, that is working. Awesome. Okay, so what I have here is a series of different data flows that I use within this sample factory. I have a pipeline called warm my ETL, and I have a pipeline called regular ETL. These are running data flows. What you can do is, if you use the TTL feature within the Azure Integration Runtime, we can stand up a warm pool of resources for you that'll be maintained for up to 4 hours. That's a setting that you can set in that time to live. And a technique you can use is you can run a pipeline that all it does is just instantiate that warm pool. And so I have a sort of almost like a dummy data flow that I call warm flow that has a file that I have as almost like a dummy file that I call warm data. All it has in it is a single value. It has like no header, no columns. It's got the number 1 in it is all it has. So it takes like 30 seconds to run a source and a sink, because remember you need a source and a sink. As soon as I run this, now I've got a warm pool. Now I can just start throwing sequential activities at it. So I set in my settings, I set my operational env is the name of my Azure IR. And that Azure IR has on it is this guy right here, a setting of 10-minute TTL. So what happens now when I look at my monitoring view for those regular runs, what happens is if I run it against the normal Azure Integration Runtime without a TTL, like what Dan had in his example, it took 5 minutes to start up the compute environments. But if I used the TTL Azure Integration Runtime, now it takes a total of 3 minutes for the entire ETL to run, and the cluster acquisition time was 2 minutes. So another great optimization way to increase your performance of your data flows is to use the TTL so you can have a warm pool. Now, one more thing I want to show you with this is there's another way also to optimize this. So let me go back to this data flow. I have to change my thing. Hang on a second. Go from here to here. Back on this data flow, another way that you can also get a similar effect is, let's say you had three different data flows. I'm going to try this again and see if this is working for me now. There we go. Yeah, you can just drag and drop your data flows and stick them on the design surface. So if I had these 3 data flows and I didn't need to run these in sequence, because these are running essentially different sets of logic that don't rely upon each other, there's no dependencies here, I can just set my pipeline like this. This pipeline would execute these data flows in parallel. And what that means is if each one of these takes 5 minutes to acquire a compute, the overall pipeline latency for compute environment is 5 minutes total. If I sequence them, so if I just do this, if I just draw a line between these guys, now it's going to be 5 plus 5 plus 5, or 15 minutes. So just taking away these dependency lines itself buys you 10 minutes back of time. These will all execute in parallel with the same startup time. And that startup time is all consumed at the same time because they start at the same time. If you want to sequence, like I was doing here, if you want to sequence these, that's when I recommend using the TTL. So you only see a 2-minute wait between each one of these. Okay, we're almost at time, and there's one more quick topic that I do want to hit on, because I did promise in the intro to show a little bit about troubleshooting. So let me quick change my view again. I'm telling you, man, I am becoming a pro at this. This is nice. Boom. So I'm going to share these slides with you all, so you'll have the links and you have some of the things I've been talking about in here in the slides as well. And in the slides, I have a link to our troubleshooting guide and to our tutorial for how to handle error handling within data flows. We're adding additional error handling capabilities in data flows to make it easier. But I have this described in a video as well that's in the link. It also shows you how you can use conditional splits to do things like work around problems that you may have when you're writing to a database. That's a very common thing, which is you could get this message back saying that possible data truncation And so you can go and you can look for that, or you can just trim your fields and you can avoid that. But we should be handling this a little bit more automatically, and we're going to be working on making that better. And I want to take out that extra quote I had there. There you go. If you're working, I'm working bottom up, by the way. I don't know why I'm doing that, but I'm working bottom up on the slide. If you are working with JSON, and you have your data is essentially a single document within your JSON file, make sure you go into the JSON settings in the source and say single document. This is another very common one that I see, where you get this cryptic error message that we are asking engineering to make better, which is it just comes back and it says corrupt record. Corrupt record is because it was trying to read. It wasn't sure if you had a single document style JSON or not, so you just tell it that you do, and that'll clear that error. These last two at the top, broadcast timeout. So broadcast timeout is what I was talking about earlier, where Spark tries to shuffle data into memory very often. If you don't have enough memory, if you're not using memory optimized or enough cores, you can run out of memory. So you can either turn off broadcasting, which is an option that's going to land very soon, or you just increase the size of your compute when you're running it. And you can run into this during debug as well, when you're debugging from a pipeline, like I've been doing today, in which case you just increase the size of your debug cluster. Last but not least, the hit unexpected execution failed. I had this in here because we were running into a lot of capacity issues or challenges in some regions during our initial response to COVID-19, and a lot of those capacity issues have been cleared, so you don't really see that any longer. But a lot of times this happens when we were not able to acquire the compute resources to execute your data flow. Details of these are in the troubleshooting guide, and then there's the error row handling at the bottom. I did it. I'm right on time, so I appreciate everybody's time today. Hopefully this was helpful and informational for you.